Okay, well, welcome to Thermo. It's a sparse day today, unfortunately. All right. So today in Thermo, we're going to dig a little bit more into thermodynamic cycles. Hopefully you had at least a chance to try and fail on the participation. Hopefully you tried and succeeded, but at least tried and failed. And if that happened, then we can talk about it afterward and we can make sure that you're up to speed on that. What we're going to do today is try to, I guess, kind of pick apart really what was the last question on that participation assignment, which was, maybe you don't remember it, but it was like, think a little bit. We don't actually use the Carnot cycle in real power plants. So why? And what do we actually use? And you maybe have a little bit of a taste of that from looking at the homework and seeing one of the systems there. But that's a little bit where we're headed today. So we'll start, I guess, as we often do, just like going over what's happening in Thermo. So this is week 6. The big thing for this week is that there is a quiz today. So make sure that you get this quiz taken and handed in before the end of the day. If you have any questions or problems with that, as always, shoot me an email and we'll work through that. But that's the big thing, quiz today. The other stuff is, at least at this point, should be relatively normal for Thermo. So there's a participation thing. This is going to be a little bit shorter one, so it'll be 5 points. If you don't, if you understand the participation, like if you understand that, you'll be set up well for doing the homework. If you don't understand that, go to a help session, come find me, find a study group, do something so that you understand that before you start on the homework. Because that's like, that's going to be the thing that is like a knowledge check. Do I understand how I'm going to approach the types of problems that I'm going to see in the homework? So make sure that you're kind of on board with that before starting homework number 6. So, right, you're going to want to make sure that you've done that early enough that you can figure out, I'm struggling with this, I'm struggling with some concept, then you can find help some way. So I would suggest, especially for this participation number 6, for the one this week, we're starting to get into thermodynamic cycle problems. They're a little bit tricky to kind of get the hang of at first. So this is what the types of problems that's going to show up on the midterm exam. So if you're struggling with this, let's make sure you're caught up to speed. So I would say start with participation number 6 kind of as soon as makes sense. At least give yourself a couple days to make sure that you can sort things out before starting on the homework before next week. So don't start this one last minute. And then I guess the other thing, the 2 like asynchronous videos this week, you'll definitely need to watch those before starting the homework. So make sure you're watching those before starting the homework. And again, some of the problem-solving strategies that are discussed in those videos are going to be things that are going to be useful to you on the midterm exam. So you'll see a little bit, there are 2 different ways of solving the same problem, and we'll go through and you'll get the same answer both ways. Part 1 is kind of probably the way that you have done it before. Part 2 is an easier way that also is a little bit more visual. So I think it's, even if you don't use, if you prefer one over the other, that's fine. You don't need to use one versus the other, but I think the second one is a little bit more visual, which I think is always nice to be able to see graphically a little bit what's happening. So that's some of the stuff that's happening today. We're going to go through and just do like a quick review of what's happening with the Carnot cycle. Right, so for Carnot, we have something, review of Carnot. we have something that looks like this, where we have, I mean, this is going to break my screen a second, but or my presenting. Just give me a second. Hopefully we'll come back up. Okay. All right, there we are. So we have a high temperature reservoir and a low temperature reservoir, or a cold reservoir, call it TC. And essentially what we're doing is we're allowing heat to flow from the high temperature to the low temperature. We're just like interrupting that flow and restricting that flow a little bit, and extracting work. So we're allowing some of that heat to flow, but in the middle we put some different pieces of equipment to restrict that. So we have a boiler, we have a turbine, a condenser, and a compressor. And there are kind of four key values, one for each of these pieces of equipment. Right, we have the amount of heat that we're putting in from our high temperature reservoir. I can make that a little bigger. The heat that we're putting in from our high temperature reservoir. The heat that we are losing to our cold reservoir, QC. Here, let me make these guys different colors so you can see them. So this is the heat from our high temp. The heat we're losing to our low temp, that's waste heat. And then we have the work that we get out of our turbine, WT, and the work that we put into our compressor, WC. We could take this and calculate the thermal efficiency, which, right, we define as kind of what we wanted over, or what we wanted over what we had to put in, like what we wanted over what we had to pay money for. So what did we want out of our system when we're trying to generate work? So our thermal efficiency is net work over the heat input, the heat we had to put into the system, which is equal to WT plus WC over QH. And I'll just write this is, so the sign gets a little tricky with this. So, right, WC is work that we're putting into the system, so that's going to have to be a negative number. We're putting it in. So I guess I don't really care. Sometimes the book has a little bit different, like weird sign convention. Sometimes they would say WT minus WC. Try not to get confused on that. Just remember, like, that's stuff that we have to put in. So that should decrease the thermal efficiency, not increase it. And the another way that we could represent this, right, because we have energy balances, we could do an energy balance on not just one of those individual pieces. We could do an energy balance on the whole thing itself. Right, so the amount of energy that we're putting in, QH plus WC equals the amount of energy that is coming out, WT plus QL. So we can do an energy balance on the whole thing and say that this also equals QH minus Q, we'll call it, how am I'm being a little backwards with my nomenclature. I'm mixing up low and cold. So QC all over QH. And we're getting from one to the other with just an overall energy balance. So this is where we get this equation for Carnot in particular. So before this, this is for any heat engine. This is for only Carnot. So for only Carnot, because Carnot is a little bit special, we can write that Q equals T delta S for Carnot. And that works because, right, this is in Carnot, all of the steps are ideal. All of the steps are reversible. So then we can write this as 1 minus T C over T H. Where we're getting that just from that top equation, plugging in T delta S. The delta S's all cancel out, and we just get that the efficiency of a Carnot cycle is only related to the two temperatures involved. This is actually kind of a cool thing. So you can do a lot of different analyses of how efficiently you could do something, a lot of different things, just from the two temperatures involved. So you can see, okay, so if I have a power plant, one way to make my power plant better would be to raise TH. Right? What is TH in a power plant? Well, it's the temperature of the hot stuff. So maybe for a natural gas power plant, that's like the temperature of combustion. So if you can if you could do something to raise that, you can raise the efficiency. Another way, which would also be good, would be to lower the cold temperature. Typically for power generating systems, that's not easy to do. Right, that's the thermal reservoir. That's where you're dumping the heat, which is usually just like the environment. So if you think of our power plant in Holland, where do we dump heat? Well, we dump it at like, outside temperatures. That's our low temp. So it's hard if you made a power plant in Siberia versus a power plant in Phoenix. The one in Siberia is going to be better because it has a lower cold temperature. All things being equal, that's going to be a better power plant. That will be a better place because it has a lower cold temperature. If you could make two power plants, one has a higher hot temperature, that one, all things being equal, will be better. So it gives you kind of a direct way that temperature plays in. This applies anytime we're trying to take thermal energy and convert it to work. So it actually applies even in systems where it's maybe not obvious. So one of the some of my research is in solar energy. If you want to understand what's the best possible solar cell that you could ever make, your T cold is ambient temperature, say like 300 Kelvin or 298, whatever it happens to be. Your hot temperature is the temperature of the sun. And you do this exact same equation and you get that the best possible solar cell that you could ever make is 86% efficient. So it's all based on what's the temperature of the hot thing that you're working with, and you're trying to convert that energy into work. What's the temperature of the cold thing where you're going to be dumping your waste heat? So it's an easy equation, but it's really quite powerful. Now the thing to remember is always use Kelvin or Rankine. So if we use Celsius or Fahrenheit, the sign of that top one, the cold temperature, usually can flip, right? If it's winter out and it's -5 degrees, the sign of that flips and all of a sudden we get an efficiency over 100%. That can't happen. So when we're using this equation, we always have to make sure we're using Kelvin, make sure we're using Rankine. Rankine is the English unit equivalent of Kelvin, where 0 is absolute 0, but a degree is the same size. So, right, 0 Fahrenheit is negative 459 something. I think, I don't know, I'm better at the Celsius one. I think 0 Fahrenheit is negative 459, or 0 Kelvin, 0, absolute 0, is negative 459 Fahrenheit. So that's 0 Rankine, and 0 degrees Fahrenheit is like 459 Rankine, but 1 degree is the same size. Okay, so this is a really simple analysis for this type of cycle, but I just maybe gave it away a little bit because we don't actually try to do exactly this. So if we think about what's happening in our system, what we have is kind of 2 steps where we're at constant temperature. And that's kind of the well, one thing, everything is ideal. But we have, right, the whole top is all at TH. The whole bottom is all at TC. Okay, so we kind of define our system by these 2 operating temperatures, and that's like the defining feature of a Carnot cycle. We don't actually attempt to do that, and let's dig into a little bit of why. I guess before I do this, you've at least thought about this maybe a little bit. Does anybody have any ideas that they at least want to throw out as to why no real systems actually try to use Carnot? Yeah, David.
Because their systems operate adiabatically.
Okay, but we can put insulation on stuff and try to make it close. We don't even try to, I mean, we do try to make things close to adiabatic by putting insulation and trapping the heat in and doing that. But we don't try to make a system where like the top is at one temperature and the bottom is at another temperature. As Will, did you have a different idea?
Yeah, so because real systems operate with some energy
Okay, so the real systems operate with energy losses. That's exactly true. So we can't be a perfect Carnot cycle, but we can't even be like an imperfect Carnot cycle. Yeah, David.
Is it because of more drastic changes in pressure in like a system?
It does have something to do with what's happening with pressure in a system like this. Potentially, yeah, Graham.
So the only thing that can change in the boiler is the volume. So it takes forever, it takes infinitely long to have it change because the temp has to come in so slowly.
Sure. So the boiler is potentially a problem. So you have to have only the volume change. In an ideal Carnot cycle, the high temperature and the boiler at exactly the same temperature. But we don't even try to make it like where the high temperature and the boiler are at a little bit different temperature so that it's not infinitely large. Like we don't even really try to attempt it. So I'll just jump to the what's happening. And we're going to think about this in context of like what machinery would we actually have to design in order to do this. And we'll think about 2 different temperature entropy diagrams. So let's think about a temperature entropy diagram. So all of the things that you thought about are true and reasons why we can't make a Carnot cycle perfect, but they're reasons, not reasons why we can't try to make a Carnot cycle. This is a reason why we can't even really attempt it. So in a Carnot cycle, okay, we have our phase boundary maybe look something like this. And what is the temperature, what does the Carnot cycle look like on a TS diagram? What shape?
A box.
A box, right? It's a rectangle. So it's going to look something like this. So we'll draw, I think this is the version that we have done before, is say we did something like this. Okay, where we're going between these 4 different points. We're going in a box, right? We have at the bottom, the horizontal arrow, that's a heat exchange. Then we have a compression where we go vertically up. Then we have another heat exchange, horizontal, then a turbine, which is vertically down. So if we think about maybe the equipment that we would actually use to do this, it might look something like this. So this is a steam turbine. If you give me a second. I hate that it always, okay. So this is a steam turbine. And let's think a little bit about what's happening between our steam turbine and kind of this, what would have to be happening in Carnot. So look back at your notes. So the turbine part, that's the vertical line on the right-hand side. So what's going into our steam turbine, as we have the TS diagram drawn, is a saturated vapor. So it's a vapor that's just about to condense. So we have vapor coming in, and then as it's going through the turbine, right, the arrow is going straight down. So what's coming out the other side is a vapor-liquid mixture, right? That's as we have it drawn. So we have a vapor coming in. We have a vapor-liquid mixture coming out. We have an actual piece of machinery that looks something like this. So in this, right, that would be, you know, coming as it's coming through, as it's coming through the center. Apparently PowerPoint doesn't like my pen, but as it's coming through the center and going from the small side of that wheel, the turbine blades, to the large side, we have a condensation process happening. So basically we have a gas coming in and a whole bunch of water is condensing out. So the reason we can't use a Carnot cycle as we have drawn it is because we can't make an efficient turbine that has that happening inside of it. So if you have a turbine where a gas is coming in and all of a sudden all kinds of water is condensing out, you have a number of different problems, like the water falls out of the system, for one, but liquid water falls out of the system. That actually does happen in real steam turbines. It's a process called blowdown. So there is some condensation in real steam turbines, but basically that's stuff that makes our turbine more and more inefficient. So we can't really design a good turbine that has condensation happening inside of it. Let's think about the other side of our system. Okay, so Okay, so now guess I can put some numbers on this so it's a little bit easier to talk about. So now as we go from 4 to 1, right, that's a condenser that's happening. And there are some problems with doing that ideally, right? If we're trying to transfer or we're trying to take heat out and condense our system, right? We're trying to run along this, that bottom there. There are problems, as you guys pointed out, with doing that ideally, but that kind of works. Like we can at least approach it. We can try to do that. So what's happening is we have steam and water coming in, and we're taking heat out, and what we have left is less steam and more liquid. So that's a process that works okay. So we'll put a check mark by that one. And now what's happening on the other side from 1 to 2, that's like a pump or a compressor. So again, if we think back to what does the actual like system look like, I'll just do this because PowerPoint's not liking me. It looks something like one of these things. These are 2 different pumps. Maybe it looks more like a compressor. But what's happening is you have some sort of blades that are spinning and compressing your fluid. Has anybody ever had like a water pump or something like that where you get air bubbles in it?
Cavitation.
So if you have, cavitation is not air bubble. Cavitation is if you had steam bubbles in it. This would be a system that has, as we have it drawn, you would have lots of that. But if you have air bubbles in a pump, like, right, your pump blades are spinning, and instead of pushing the liquid, you just compress the air, and the pump doesn't work very well anymore. It kind of spits and sputters and doesn't pump well at all. Right, you have to prime the pump. You have to fill it up with water first, and then you can have it actually pump. Right, if you try to just start it with air and a little bit of water in it, if it has a bunch of air bubbles, it doesn't actually like suck water up and pump it out the other side. You have to fill it up with water first, then you can turn it on, then it will actually pump. So that's kind of what we're asking our pump to do on this side. So here we have a pump. Now we have what we have coming in is a vapor liquid mixture. So it has vapor in it and it has liquid in it. So we have a mixture of a gas and a liquid, and it's just functionally hard to design a compression system that works with that. Because gases, you can design something that works just with gases. You can design something that works just with liquids, but when they're mixed, because their properties are different, it just is, you just can't do it. So to design an efficient compressor / pump with a vapor liquid mixture. Okay, and then the last part is a boiler. We're boiling something at constant temperature, constant pressure. That works just fine. So we can do that. But we have these 2 pieces, like 2 of our 4 pieces of equipment we can't make. We just can't make them. So you say, why don't we not deal with, why don't we, change our system a little bit so we don't have vapors and liquids? Why don't we do something like this? Option 2. We still want to make Carnot or something close to Carnot because that's the best. So Okay, so why don't we do something like this? Okay, so now what we have happening is, let's start at the same place we did last time at 3 to 4, that turbine. What we have happening is we have a gas turbine, right? We have steam coming in at high temperature, high pressure, and it's leaving at lower temperature, lower pressure. It's leaving as a saturated vapor, but it stays gas, and it stays gas the whole time. So that process works just dandy. So we fixed one of our problems. Here from 4 to 1, right, that was the condenser. Nothing has really changed about that. We have a gas coming in and we have a liquid coming out, but we can design condensers that do that. That works just fine. Okay, now what's happening from 1 to 2 is we have a liquid coming in, the saturated liquid, and we're compressing it. And the temperature, right, the entropy is staying constant, but the temperature is going up from our low temperature to our high temperature. So we've avoided the problem of having a mixture of vapor and liquid, but this still doesn't work. Okay, why doesn't this work? Well, it's because liquids don't really change much when we change the pressure. So let's look at Cat 3. Okay, just to have a sense of what's happening. So hopefully you can see the numbers. Otherwise, I'll shout out what we have. We have water. So I'm just gonna pick out random numbers. We're gonna say, right, what we have coming in is water at, I don't know, 20 degrees Celsius. What's the pressure? Say 10 kilopascals. Okay, so we have our properties of water. For this process where we're having an ideal pump, right, what would happen, this would be a delta S equals 0 process. So we could figure out, I don't know, how much are we gonna compress it to 1,000 atmospheres, let's say. That's a really high pressure, 1,000 atmospheres. So we'll assume that we're compressing it to 1,000 atmospheres, but the entropy has to stay the same, right? Delta S equals 0. So let's do this. So now we know pressure and entropy. So the entropy is going to stay the same as it was coming in. The pressure is going to go from 1/10 of an atmosphere, 0.01 megapascals, to 1,000 atmospheres. 1,000 atmospheres, 100 megapascals. And let's see what happens to our temperature. So coming into our pump, our liquid had a temperature of 20 degrees, and we compressed it 10,000 times, and coming out of our pump, our liquid has a temperature of 21.95 degrees. So we got 2 degrees. So when we compress liquids, and we'll talk about this more in these 2 asynchronous videos, liquids don't change properties that much as we compress them. They don't change temperature that much. That's different than gases. If we take a gas, if we have a gas coming in and we compress a gas, we do actually change the temperature quite a bit. We'll run into that later in the course when we talk about gas cycles. But for liquids, nothing much changes. It does change temperature, it does change enthalpy, it does change specific volume, it changes all of those things, but not very much, and not enough to give us an efficient cycle, right? If You know, we're thinking we want a large, right? This is our T cold. This is our T hot. We want that delta to be as large as possible. And if we're pumping a liquid, it's just not possible to get a big temperature difference. We compressed it 10,000 times and we got 2 degrees. We want like hundreds of degrees. So it's just not possible to design the stuff to be able to do that. So this, we can't. We can't get a large delta T with liquid pumping. Right, we only got 2 degrees for a 10,000x compression. And we have some of the same problems going from 2 to 3, although it's not super clear. While we're in this section, that section works fine where we're heating something from a liquid into a gas. We're just boiling it. This section, so really high pressure, and there is relatively low pressure. So as we're moving across, we're trying to keep the temperature the same, but our pressure is going down like crazy. The only way that we can do that ideally is if we're also extracting work. So we have this kind of a weird process going on. And the same thing here, we have here is pressure. The pressure is decreasing as we go horizontally on that section, right? Once we're just a gas. So both of those systems, we would have to have, basically, we would have to have a turbine integrated into a heat exchanger that could both extract work, lower the pressure, and keep temperature the same. And it would just functionally be really hard to design, right? It's easier to design a turbine that we just strap some insulation around it, keep it close to adiabatic, than it is to have a turbine where we have, I don't know what you would have to do even. You'd have to put like water pipes inside of it to keep all of the stuff at the right temperature, and you'd have to have some crazy heat exchange process happening while you have these big blades spinning, and it would be wild to try to design something like that. It's easier to design systems that are like one functional, right? Something that just is for heat exchange. We can design that pretty easily. Something that's just for extracting work, we can design that. When you have to mix both of those systems into the same thing, your system just gets really ugly. And it's something you can't design efficiently. Okay, so you maybe have seen a little bit, hopefully you've seen a little bit what we actually do in a better real power plant cycle. And the problem is it looks close, and that's for a reason. It's supposed to look close because, right, we want to be doing Carnot. We just can't. So a better real power plant cycle is the Rankine cycle. Come on, buddy. I don't know why this program always does that. Okay, and in a Rankine cycle, so a Carnot cycle, we wanted the top of our system and the bottom of our system to be at constant temperature. For a Rankine cycle, we're going to change that, and we're going to say the top of our system and the bottom of our system are constant pressure. Okay, but it's going to look basically the same. So we have a TH boiler, we have a turbine, that comes through a condenser. That's a really ugly one. Goes through a pump and then back into the boiler. We have a work going into the pump, work coming out of the turbine. So let me make these blue so that we can see them. And we have heat going into and out of our boiler and out of our condenser. Okay, so the schematic looks essentially exactly the same, although we have on the left side we have a pump. It's easier to tell the difference in the temperature entropy diagram, right, where Carnot was a square. Rankine doesn't look anything like a square. So this is entropy, that's temperature. Okay. Our phase diagram still looks the same as it did. Now what's happening? Okay, so we're starting. We can label this quick. If we label it the same, we'll call that 1, 2, 3, and 4. The same as what we did previously for Carnot. We're going to start and make sure that we're pumping just a single phase thing, so just a liquid. And what we saw is when we compress a liquid, we change the pressure, but the temperature hardly changes at all. So we're going to have from 1 to 2, we hardly go up at all. Temperature. I expanded that way more than it actually is in real life, just so that we could be able to differentiate between the two dots, right? We hardly change temperature at all. We do a little bit. Okay, and then we're going to feed that, number 2, into a boiler. So what's going to happen is we're going to heat up a little bit, and then we're going to start to boil. So we heat up here, and then we get to there, and then we start to boil. But we're not done yet. We're actually going to let it heat up beyond the boiling point a little bit, right? Because we couldn't take this. We have problems designing our turbine. We couldn't have this vapor liquid mixture in our turbine. So we want to make sure we have only vapor in our turbine, or almost only vapor. We can have a little bit. So we're going to take this, and the outlet of our boiler is going to be superheated vapor. Then this is going to be fed into our turbine. And this is our heat exchange process. Okay, so it looks a little bit goofy. It's hard to draw a little bit. I did an okay job. Right, so the key points, it's basically the same, but this is all at high pressure. And this whole bottom part is all at low pressure. And that's really the key difference between a Rankine cycle and a Carnot cycle. The Carnot cycle, we had two temperatures. We had the top half of our system at high temperature. The bottom half of our system was at low temperature. A Rankine cycle, we have the top half at high pressure and the bottom half at low pressure. And that works because, okay, if we think of what's happening in our pump just has to take a liquid from low pressure to high pressure. That's what pumps do best. Our boiler has to take in a liquid and heat it up, boil it, turn it into a gas, keep heating it, but it's all at one constant pressure. It's really hard to change pressure in a boiler system, right? A boiler is typically like something flowing through pipes and something else heating it. It's really easy to do that if everything is at the same pressure. If you have to have different pressures in different parts of the system, it's basically impossible to design. So constant pressure boiler works great. And then the turbine, we have superheated vapor coming in, and we're using that, and we're extracting work, and vapor is coming out. It's easy to design a turbine that works with one phase, like just a gas or just a liquid. It's impossible if we have too much of both. So the turbine works great. And then the condenser part from 4 to 1 is similar to the boiler, where we're taking in a vapor and we're turning it into a liquid, but everything is happening at the same pressure. It also, as I have it drawn here, the condenser is operating at the same pressure and the same temperature. But that's not, it doesn't have to be that way. It is that way in the ideal Rankine cycle. But we'll talk next class about kind of little modifications that we can do on this. Because if we look at our temperature entropy diagram, it is no longer a square. Right? That was kind of the key thing that that we know about the Carnot cycle, is we have this temperature entropy diagram that's a square. We could shade in things like the high temperature and the low temperature heat, and the amount of work was the size of the square. The same kinds of things apply to this graph, where we could shade in QH and QL, and the size of the thing is the work. We'll go through, when you go through and look at the temperatures in the system and compare a Carnot cycle to a Rankine cycle, a basic Rankine cycle like this is really bad. So there's kind of a lot of extra work that we have to do to say, how can we get from this? We can design all the equipment now, which is good. Like, we can actually do it. But how do we get closer back to a Carnot cycle? And that takes, there's a lot of modifications and thought that goes into how do we make something that looks like this? How do we take it and make it more square? What kind of modifications, what extra steps can we add in order to do that? Just to give a little bit of a feel for where you find some of this in the last minute or so that I have here. Here's a normal fossil fuel power plant. So if we look at what we would have here, okay, so over here you find the pump. Okay, so that's taking a liquid, it's pumping it up. Here you have a boiler. The heat input for your boiler is burning fossil fuels, whether that's coal or natural gas or something. It's the heat from burning fossil fuels. Then you're taking those gases and bringing them into the turbine. The turbine is connected to an electric generator. So you have these spinning blades in the turbine. That's spinning an electric generator, which is what's actually giving you your electricity. The outlet of the turbine goes into the condenser. There's some sort of heat exchange process. So this is your Q low. So if you go and look at the Holland power plant, you'll see these big stacks kind of back behind it. Those are the cooling towers. That's how our power plant supplies the low temperature heat. Different power plants do this differently. So when I was a graduate student at Notre Dame, they had a power plant on campus, and they got their low temperature heat by just taking water from a little lake on campus and running that through their system. So in the winter, the lake never really froze because they were using that and kind of dumping their waste heat into the lake and using that as a thermal reservoir. You can use cooling towers, you can use different systems like that. But you can see here, right, this section there, that is the Rankine cycle. And there's other stuff around that to actually make electricity and make the system happen. A nuclear power plant is the same thing. Nuclear power plant, we just have a different heat source. So we have our pump here. Our heat source is now nuclear fuel. That's what's boiling our water, bringing it through our turbine. We still have our electric generator. So this is our Rankine cycle right here. A solar thermal power plant, same thing, different heat source. Right, here's our Rankine cycle right here. And we have some extra stuff going on. We can still have cooling towers. We have an extra stuff going on over here where we're capturing thermal energy from solar. A geothermal plant, same thing. Here is our Rankine cycle. A geothermal plant, the other ones that I showed all work with high temperature heat sources. A geothermal power plant has a pretty low temperature heat source. So it has to use different fluids. It can't use water, but it operates off the same cycle, the same pieces of equipment. We'll follow up with this and continue to talk more about it next week. In class, you'll get a chance to explore some of this a little bit. I just want to show this last slide because, right, this is like my solution strategies for how to think about these problems. They're multi-step, but they're the same types of problems you solved in, that we've solved throughout this class in chapter 4 and in chapter 7 and all the times we did this. So basically, it's a step-by-step process. You want to find a single spot to start. That's a spot where you can look up everything in the tables or look up everything in Cat 3. And then you're going to basically move around the system from there, step by step, using energy balances. So draw a good scheme, label it, start a place that you know everything, that you can look stuff up, right? Everything meaning like you know 2 things and you looked up the rest. And then you're going to work step by step and say, what happens from this step to this step? Well, that's a constant pressure step. That's a constant entropy step, whatever is happening. This is a non-ideal step, so we have to solve it like that. We have to go back to isentropic efficiency, however it is that you have to get from, one side of the piece of equipment to the other side. And then once you know what's on the other side, then you can look at the next piece of equipment and kind of continue to work your way around in a circle. We'll get some more practice actually doing that. That's all the time that I have for today. So I'm going to hang around a little bit. If you have any questions, especially about this week's homework or participation or any of this stuff, I'd be happy to hang around and answer those.